Welcome to our presentation of our system here. We are designing an automatic tempo detection system. The reason why we chose to make this system was because of some conversations I'd had with my brother, who is a performer. He's a musician, and he told me about a dilemma that he has when he's on stage. He uses a lot of different musical things to help his music, and devices and pedals for his guitars and effects for voices and whatnot. And some of these effects are synchronized to the tempo of the song. Now, when you're performing music, that tempo, it can change unless you're listening to a pre-recorded metronome or tempo track or something like that, which a lot of musicians don't want to do because it takes away from the feel of the live music. So we thought that he has for instance a delay pedal that he can go up and he can tap the tempo, and it will adjust the delay to have the delay at a rate the same as the tempo of the music. So we thought, wouldn't it be much nicer if instead of having to do that, we could just automatically discern the tempo and send that to delay pedal or any other effects, and just have that happen automatically. That was kind of the reason why we decided to make this. Now, what we're going to demo for you today here is the light sequencing part of this. This takes in sound through a microphone right here, a very small MEMS microphone, and then it processes the sound through a sigma delta modulator, which is a filtering system, and then it uses fast Fourier transform and as well as an extremes detector to find the tempo of which is basically the distance and time between the two extremes, or between a certain frequency, which is found with the fast Fourier transform. And then it'll sequence the lights based on that tempo. We are having some problems with the microphone at the moment, so we're not able to demo that portion for you right now, but we will show you some of the lights and some of the other parts of our system here.
Okay, so the lights are just hooked up to the GPIO ports through resistors and wires, and the ports we used are GPIO E, B, and H. So going from E is your voltage high, and then H and B are your voltage lows. So that, and each individual pin controls a different column or row. All of the rows are controlled by port E, and port B and H combined take care of the columns. So you only see the rows changing, and that's because just as we were having problems with the microphones, the columns were giving us some difficulties as well with when we tried to change it in sequence as the program was running, that it didn't behave as the logic we would give it, and so we know there's a problem, but we're not really sure what. The ports are configured as general purpose outputs with pull-up resistors, and they are a pull-up, pull-down for GPIO-E. B and H are set up as open drain instead. Then the LCD is also being used, which will tell you your current settings, and the settings are your sequence you're on, the brightness, and whether it's active or inactive, on/off. In the order it gives you: sequence, number, brightness, number, and then A for active, I for inactive. We currently have 10 different sequences set up. So going to just one of the other ones, since it's kind of carefully there. So as you saw, it just simply changed what sequence it's going by, and you can see the number change here for what sequence you are on. And this makes it very quick and easy and simple. If currently, to show it will actually work with the tempo, we've set it up to work when you change the brightness, it also changes the tempo, so that we can show that once we do get the microphone working, that it will integrate nicely and actually do what we want it to do completely. And then turning the inactive state, and then back to active. There we go. Yeah.
So that's kind of our design. There's a couple other parts of this that we were looking to kind of implement, and we'll make a new video at that time. Thank you very much.